Chapter 8, Non-Electrolyte Solutions, Section 8.3, Thermodynamics of Ideal Solutions. When a chemical species I in a solution reach equilibrium with its vapor in the gas phase, we have this equation. The chemical potential of I in the solution equals the chemical potential of I in the gas phase. In the gas phase, we have its partial pressure, P sub I. And the chemical potential of this species in the gas phase is equal to the standard chemical potential of this species plus RT times the natural logarithm of its partial pressure of P naught over P naught. We proved this equation before. For 100% pure I, we have a similar equation. Over here we have mu sub I star. Star denotes pure. On the right hand side, we also have the standard chemical potential plus RT times the natural logarithm. Over here we have the pressure of pure I in the gas phase over P naught. So these two equations are similar but a little different. The first equation is for the solution of I. The second equation is for pure I. Now we're going to take the difference between these two equations. We use the left hand side, this minus this. Alright, we have the left hand side of the equation here. Now we use this minus this, and you can see the standard chemical potential cancels. We have just RT times natural logarithm of Pi over Pi star. P naught and P naught also cancel. So we have only Pi over P star here. And because Raoult's law states that Pi is the mole fraction of I in the solution times the pressure of pure I, then this ratio is simply the mole fraction of I. We have a simplified equation for the chemical potential of species I in a solution. It equals the chemical potential of pure I plus RT times the natural logarithm of the mole fraction of I. Since this mole fraction is always the 1, the chemical potential of species I in a solution is less than the chemical potential of pure I. When species I is mixed with another chemical, its chemical potential decreases. By how much? We can calculate this chemical potential decrease given the mole fraction and temperature. And consequently, its Gibbs energy decreases. The change is, again, over here. It's just N sub I times RT times the natural logarithm of X sub I. And we can rewrite this N sub I, the moles of I, as N times X sub I. N is the total number of moles of all components. And then we have this equation for the Gibbs energy change of species I upon mixing. What if we have several pure liquids being mixed? Then the total Gibbs energy change due to mixing is nRT times the sum of xi ln xi. So over here we just sum up this term for every single liquid, and we get this equation for the Gibbs energy of mixing. Again, N is the total number of moles of all species in the solution. R is the constant, the ideal gas constant. T is the temperature. X is the mole fraction. Now we have this expression for the Gibbs energy of mixing over here, nRT times the sum of xi ln xi. Now let's look at this differential of G. dG is negative S dt plus VdP for a single species. From this equation, we can take the difference before versus after mixing. And then we have the differential of delta G equals negative delta S dt plus delta V dP. So delta S denotes the change, and over here we're looking at the mixing. So we're looking at the change of Gibbs energy after mixing. This is the change of entropy after mixing. This is the change of volume after mixing. Given this equation, if we hold pressure constant, dP is 0, and then delta S mixing is negative delta G mixing over delta T. So it's the first derivative of delta G mixing with respect to temperature on the constant pressure condition. And we plug in this expression over here. We can see this is proportional to the temperature. The proportionality is over here nR times the sum. Over here we have nR multiplied by this sum of xi ln xi. We do need to copy this negative sign here. Alright, now we have expression for entropy of mixing. This is always greater than 0 because we do have a negative sign here, and ln x is always negative. Now let's derive delta V mixing. Because this delta G mixing is independent of pressure, none of this either parameters or variables depends on pressure. So delta mixing is independent of pressure, and then delta V is the first derivative of delta G over P, and then this part is 0 because delta G mixing is independent of pressure. We can also compute or derive the enthalpy and internal energy of mixing. Delta H mixing is delta G mixing plus delta TS mixing, and this is delta G, and over here this is delta TS. Because T is a constant, we can take T out, and we have delta S mixing over here, and then we get this second term. You can see the first term and the second term cancel, so we have 0. The enthalpy of mixing is 0. The internal energy of mixing is enthalpy of mixing minus PV of mixing. But we learned there's no volume change over here. We learned there's no pressure change. So delta U is 0. Well, it does make sense because we're talking about an ideal solution. In an ideal solution, if we have two components, the AB interaction equals A interaction equals BB interaction. Upon mixing, there's no change in the amount of attraction or repulsion felt by any particle in the solution. So that's why delta U is 0. Now let's look at one numerical example problem. 8.3.1. Calculate the change of Gibbs energy, entropy, internal energy, enthalpy, Helmholtz energy after we mix 0.2 moles of A, 0.4 moles of B, and 1.4 moles of C to form an ideal solution at room temperature under isobaric condition. First, the total number of moles is 2 moles. The mole fractions are 0.1, 0.2, and 0.7. We double check here, make sure the sum is 1. And then we compute delta G mixing. This is the equation. It's nRT sum xi ln xi. N is 2, R is 8.3, T is room temperature. And over here we have 0.1 ln 0.1 for A, species A, 0.2 ln 0.2, species B, 0.7 ln 0.7, species C. This is just a numerical calculation. We get negative 4,000-ish joule. That's the Gibbs energy change after mixing. And now we can compute the entropy of mixing. It's this expression. And you might notice this expression is simply this expression divided by negative T. So really it's just negative 4,000 divided by negative temperature. We get 13 joule per Kelvin. That's the entropy of mixing. So again, if you compare this expression for entropy of mixing In this expression, for Gibbs energy of mixing, they differ by a factor of negative t. Now delta V mixing is 0, delta PV mixing is 0, delta H mixing is 0 for ideal gases. You can double check this calculation, plug in all the numbers. You have delta G over here, you have delta S over here, you have temperature over here. Plug in all the numbers, you get 0. Delta U is also 0 because delta H is 0, and P and V are all remaining constant. Delta A is equal to delta G. Again, it's because delta PV of mixing is 0. And this is because neither pressure nor volume changes during the mixing. So delta A mixing is delta G mixing. It's negative 4,000-ish joules.